Okay, welcome back. So I left you looking at determining the distance to a particular Cepheid variable. So if you go back to the plot, so 15 days, assume it's a type 1. You can read off here, it's about minus 3.1-ish or something if you do it with a ruler. You can see that, if you do get the wrong type of Cepheid, then you're going to be wrong by quite a significant factor. So that was important, and that did cause problems very early on with this method. But these days, it's not such a problem. And if you do a whole sample of Cepheids in a particular galaxy, if you can find many of them, then they will obviously divide out into these two curves quite easily. So here, so you've got the intrinsic absolute magnitude. We're ignoring extinction, so you can just solve this equation for D, and that's all there is to it. Okay, so you can see here that with the parameters I gave you, then you come out with about 15 megaparsecs, which indeed is the distance to the Virgo cluster of galaxies. So you can see that, but in order to do that, you need to be down at, have like the Hubble telescope and have this limiting magnitude of about 30 in order to well characterize objects that are just about brighter than that limit. So here at around 28th magnitude. Okay, so again, you needed the sensitivity of the Hubble Space Telescope and its angular resolution to resolve individual stars in order to do this experiment. And as we shall see in the next lecture, it basically solved the debate for the Hubble constant. Okay, so as I alluded to in workshop 4, the Virgo cluster of galaxies is still basically the kind of nearest cluster of galaxies. So if we want to go much further than that, we're going to have to find something other than Cepheid variables to do the job, because we're already there at the limit to Cepheid variables. So if we want to look out into the much more distant universe, like the sort of picture behind me here, and find the distances to very distant galaxies, and also explore the realms of cosmology, where you're really looking into the distant universe and getting the measure of it, we need something else. And this takes us to the other type of standard candle that I want to talk about, which again, initially sounds even more counterintuitive, because this involves the use of supernovae explosions. Okay, so we've talked about supernovae a couple of times now. So here we want to focus in on the other type of supernova explosion that we haven't talked about much yet, which is the so-called type 1a supernovae. Okay, so if you recall, then this is the other type of supernovae where you take a white dwarf star, which has a very specific upper mass limit to it, and you need to be able to add mass to it until you just push it over that limit, and then it explodes as a supernova. Okay, so that's what a type 1 supernova is. Now, as I alluded to before, this maximum mass for the white dwarf, over which, if you push it, then it'll explode, is basically set by just fundamental atomic physics constants. Okay, so it is a universal upper limit to the mass, no matter where you are in the universe. So that when they do explode, the idea is that they will always explode in exactly the same way, because it's always precisely the same mass that is going boom, basically. So even though this is an extraordinarily energetic explosion, which you might think would be a very poorly calibratable event, in fact, the idea is that it is very, basically there will always be the same intrinsic brightness, because you're basically blowing up the same amount of mass in the same way each time. Okay. So it's like a controlled explosion. And so the parameter that you want to measure, remember that these supernovae, they're not pulsating stars, they're just going bang once and that's the end of it. So they'll go up in brightness, a peak, and then come down again. And because we saw the light curve before, but I think we'll see them again in a moment. So there's a particular point in that light curve, which is obviously very measurable and calibratable, and it's the brightness at the maximum light. Okay. Of course, this is also a good thing because supernovae are incredibly bright. Okay, we looked at that before. So these are intrinsically extremely luminous objects, which means we can see them a long way away. And obviously, if you can spot them, they stand out obviously because it's an exploding star, right? So it's a one-off event. Okay. So they do tick all of those standard candle boxes. Okay. They are intrinsically bright, they are easily recognizable, and if you can spot the type 1A ones and separate out them from all the other type of supernovae, like the exploding single massive stars, which are obviously not calibratable at all because you'd have to know the original mass and everything else. But if you can spot the type 1As, then you're in business. So yeah, extremely bright. So we can see them out to basically cosmological distances. So cosmological distance means, you know, a significant fraction of the size of the universe. So just to remind you, well, I don't think I've shown this before really, but we've seen something similar before. So how do you know, how does the white dwarf star that we're trying to explode gain mass? Well, it will do so in an interacting binary system, so a close binary system. So if you've got a white dwarf here and you've got a companion star, especially one perhaps that's started to evolve itself. So this star will have evolved first. So this would have been the slightly more massive star. So, you know, any kind of main sequence star up to 8 solar masses would have gone through its evolutionary phases, its planetary nebulae, ejected its outer envelope and left behind the white dwarf. Sometime later, its companion star, which was a lower mass star originally, will also start to evolve into a red giant, and at that point often it will start to, the white dwarf will start to pull material from the expanded star, and because of the orbit it will spiral down as a so-called accretion disk onto the white dwarf, but that will add mass to the white dwarf. Okay? And if you keep adding mass, keep adding mass, keep adding mass, at some point, boom, it will explode as a type 1A supernova. Now, you know, this is a tricky operation to find them though, okay? It's not like Cephids where they've got periods of days and they're fairly reliable and repeatable and predictable, okay? This is a one-off event that is totally and utterly unpredictable. So how do you find them? Okay. Well, I mentioned that the supernova rate in our galaxy is 1 in about every 30 years or so. Okay? And only a small fraction of those would be type 1A supernovae as opposed to the type 2 supernovae. So, you know, what are you going to do? You're going to sit around and stare at one galaxy for 100 years and hope that a type 1A supernova goes off? Well, that would be a bit inefficient. So in order to find these objects, you need to monitor many galaxies. You know, you'd be wanting to look at hundreds of galaxies a night, basically, and keep monitoring them nightly as well, because the right, apologies for that. So you need to constantly image hundreds of galaxies every night. So telescope going around, taking an image of a galaxy every night at high resolution as possible. And then you might have enough statistics and chance to actually catch these explosions happening. Okay. And as we shall see probably in the next lecture, this has become a kind of a major industry these days. In fact, people doing this have won the Nobel Prize for doing this. And so this is, there's a lot of telescopes just purely dedicated to finding these supernovae now, because it's going to tell us so much about the universe. Okay, yeah, so the reason you need to do it every night, okay, if you recall the supernova light curves, is that you've got to catch them before they get up to their maximum light, because that's the point at which that's the bit we're going to use as the standard candle, if you like. Okay, so the apparent magnitude at maximum light, or the absolute magnitude at maximum light, is what we're using as the standard candle measure. And these objects will come up to their maximum light in just a few days. So you have to catch them early, or you've missed the chance. Okay, so here's a little test for yourself. So this is the kind of idea with looking for supernovae. You've got two pictures of the same galaxy, actually taken with quite a small telescope, this one. Anybody spot where the supernova is? So you need to compare these two images. So this is another part of that process, is compare the two images of the galaxies and look for any new source that has appeared. Okay. So if you look here, okay, there's what looks like a star, okay, but it wasn't in this image, okay. And so, you know, if this image was taken one night and then this one was taken in the next night, and you difference the two images, everything else disappears, but here it looks like there's something new. Okay. In fact, I seem to have just spotted something new over there as well, but anyway, maybe it was unlikely if there's two, but anyway, this is the one that's clearly didn't even seem to be there at all before. So this new object appeared. So that is a supernova going off in that galaxy. You can see it's in the spiral arm here as well. So maybe it's not a type 1a, because you probably wouldn't want it to be in the spiral arm for that. But this is how you can spot supernovae. Okay. And here's a couple more examples. Okay. So this is one of these, again, sort of I thought was rare occurrences, when you've got two supernovae going off in the galaxy at the same time. So here's one that's fading. Okay, so you can see that it's very bright here and getting fainter here. But in the outskirts over here, a new one has just appeared. Okay, so another new supernova is just appearing over another part of this galaxy. Okay. So again, you'd have to characterize each of these to work out what type of supernova they are. Okay. And you can do that by looking at their light curves. Okay, so first of all, you'd need to plot out their light curves as a function of time. Okay, so their apparent magnitude as a function of time. And this is the point in the light curve that you're looking for, the maximum light. Okay. But you are going to have to follow them for a long time, okay, as they fade, because as we briefly touched upon earlier, then the shape of the light curves for the two different types of supernovae are different. Okay. So the type 2 supernovae has these distinct sort of bumps in it, okay, and this is due to the fact of lots of heavy elements in the type 2 supernovae from the sort of exploding iron core of the massive stars. They've got a lot of radioactive elements, so this very distinctive shape here is where the entire fireball is actually powered by the radioactive decay of a whole load of nickel in the exploding object, which has a very particular half-life, which matches exactly this shape of this curve. So they're very distinctive, whereas the type 1As are just an exploding white dwarf, which is basically made of pretty much pure carbon and oxygen, okay, as a leftover from the helium burning of low mass stars. There are no heavy elements in there at all, so it's just an exploding ball of carbon and oxygen, and that doesn't have any of those different shapes in it. Okay, so that if you can follow them down to this point, then you can distinguish which type you're in. Okay, and measuring those gets you out to much further away, so very distant galaxies. So standard candles are used to, basically it's an indirect method. It's not like the trigonometric parallax method, obviously, which is a purely geometric method that gives you the distance directly. So here we are relying on these calibrations of the standard candles. So that's what we mean by an indirect method. And another key component of all of this is the idea that the Gaia satellite will measure very accurate parallaxes for lots of Cepheid variables in our galaxy and really put that method on a much more precise foundation than it has been previously. Okay, and then the type 1As get you much further out into the universe. And again, if you want to read around the subject a little bit, you'll be able to read about this idea of what's called a distance ladder. Okay, so this is the idea that you use various methods to gradually try and get you further and further away. Okay, so you can use the trigonometric parallax method to calibrate the Cepheid variables. Then for nearby galaxies, you can find galaxies that have got both Cepheid variables in them and type 1A supernovae. So you can use the Cepheid variables to calibrate the type 1A supernovae. Okay, and then once you've done that, then you can use the type 1A supernovae to go as far as you can possibly see them. Okay. And there are lots of other distance methods that you can read about, but in this module we will only worry about these two. Yeah, so it's the type 1As that take us out to cosmological distances, and that has unlocked a whole load of incredible discoveries. So obviously the fact that the universe is dominated by dark matter, but it was the monitoring and studying of type 1A supernovae to cosmological distances that discovered the idea of dark energy, which I'm sure you might have read about as well. And hence, that's why the teams who set up these monitoring programs for type 1A supernovae won the Nobel Prize, because they unlocked this new discovery of dark energy in the universe. Okay, so let's leave it there for now, and next time we'll talk about that idea of dark energy. Okay, oh, sorry, not dark energy. We will talk about the Hubble's law and using these standard candles for that. Okay, apologies for that.